Jai Hind. Myself Ravindra Kumar, Assistant Professor in EN Department, AKGEC Engineering College, Ghaziabad. Today I am presenting the topic DC circuits in the subject Basic Electrical Engineering. So in this topic, I will be covering different subtopics like the circuit elements, what are the various circuit elements, energy sources which are connected in the circuit, different types of energy sources, plus Kirchhoff's laws which are applied to the electrical circuits. So if we see it, these are the various contents in this circuit elements, that is one of the content that I will cover in this. Then energy sources, various types of energy sources, and Kirchhoff's laws. These topics will be covered under this discussion. So first we go for the circuit elements. So if we see it one by one with the definitions plus the examples and other things. First we have linear elements. So what is linear element? A linear element is an electrical element with a linear relationship between current and voltage. And these elements they follow the property of homogeneity and additivity. So one thing is it is having a linear relationship between current and voltage. Another thing, it is following the property of homogeneity and additivity. Example for this is resistance, that is the most common example for the linear element, and other example they include inductance and capacitance, they are also the linear elements. Now if we elaborate it, what is homogeneity and additivity property? So homogeneity means linearity property, that time output is directly proportional to input, that we call homogeneity property. Like for example here resistance, which is the common example for a linear element. So in that we know current output is directly proportional to voltage input. That means when some voltage is applied across resistance, then a current passes through that resistance and that current is directly proportional to the applied voltage, or output is directly proportional to input. So that is homogeneity property. And additivity property, according to that, what we have now, we can write this equation I equal to V by R. That is the equation where R is the resistance, V is the voltage applied across it, and I is the current. So suppose I apply a voltage V1 and I get current I1, which will be V1 by R. Next time I apply a voltage V2, which is corresponding to that, I get a current I2, that is V2 by R. Now third time, if I apply linear combination of these two inputs V1 and V2, so that means I apply this voltage as input to this resistance, that time the current suppose is I, so that will be given by V1 plus V2 by R, and if we see it, it will be equal to I1 plus I2. So that is known as additivity property. So in linear element, these two properties, one is homogeneity, that is this output is directly proportional to input, and second one is additivity, that is this that I have explained. So if these two properties are satisfied, then the element is linear element. And the examples that we have seen, what are the examples for this? On the other hand, we have non-linear elements. So it is simply in non-linear element, these properties are not satisfied. So it is the element in which there is no linear relationship between input and output. Plus these elements, they do not follow homogeneity and additivity properties. So like for example diode, in this there is no linearity property, since current is not directly proportional to the voltage applied across the diode, or it is a non-linear function of the voltage. So that's why diode is an example for non-linear element. So that way we have linear element which may be connected in the circuit, and also the non-linear element that may be connected in the circuit. So that way it is there. Next we have another category, active elements. So these are the elements which are responsible for generation of or production of electrical energy in the circuit. So they are known as active elements. The example for this, batteries, generators, transistors, operational amplifiers, vacuum tube diode. All these are the examples for active element. Like batteries, what we have in that chemical energy that is converted into the electrical energy with the help of a battery, so that it is the source of electrical energy and it is active element. Similarly, generator that converts mechanical energy into electrical energy, so it is also an active element. Similarly, like vacuum tube diode, in diode what we have, there are two terminals, anode and cathode. Anode is having positive potential with respect to cathode, so, and when cathode is heated up, the electrons which are available in majority on the cathode, they are attracted towards anode due to the positive potential on anode, and that way electron flow is there in a diode, and this is passing through the circuit in which the diode is connected. So, that means electronic current is passing in the circuit, so that electrical energy is passing in the circuit with the help of this. So, that is why vacuum tube diode, that is also an active element. On the other hand, if we see passive elements, so that is just opposite to the active element. These elements, what they have, either they consume or dissipate rather than producing the electrical energy. So, such elements, they are known as passive elements, and the example for this is resistance, inductance and capacitance. Since a resistance that converts electrical energy into heat energy, while inductance and capacitance, what they do, they store electrical energy inside them. Inductor stores electrical energy in the magnetic field, while the capacitor stores electrical energy in the electric field. So, they are coming under the category of passive elements. Next, we have unilateral elements. In unilateral elements, what is there? The relation between voltage and current, that is not identical or that is not same for both the directions of current flow. That means the relation between voltage and current is different for the two different directions or two opposite directions of current flow, and the example for this is diode and transistor. Like we know, in diode we have, this is the symbol for diode. So, this is anode and this is cathode. So, when anode is having positive potential with respect to cathode, so that time diode is forward bias and current is passing through the diode easily, and there is certain relation between voltage and current that time. But on the other hand, if we reverse bias the diode, that means I make opposite polarity on anode and cathode, that means like this. So, that time a very small current or no current passes through the diode, and plus the relation between voltage and current, that is also different. So, that diode is working as unilateral element, it is not a bilateral element. On the other hand, bilateral elements, in these voltage and current relation, that is same for both the directions of current flow, and the example for this, resistance, inductance and capacitance. These are the examples for bilateral elements. Since in these elements current can pass in both the directions easily without any type of problem, plus the relation between voltage and current, that is same in both the directions of current flow, not like a diode in which the relation between voltage and current, that is different for two opposite directions of current flow. So, that is why RL and C, they are coming under the category of bilateral elements, while the diode is coming under the category of unilateral elements. So, these are various types of elements that we have discussed: active element, passive element, unilateral, bilateral element, linear and non-linear elements. So, a circuit that is consisting of all these elements or some of these elements that may be there, which are connected in the circuit. So, or in other words, we can say any circuit is a combination of various types of elements, which may include active and passive elements, unilateral and bilateral elements, linear and non-linear elements. That is the way for defining any circuit. Next, we have different types of energy sources. So, basically there are two types of energy sources, one is voltage source and another one is current source. Now, in this again we have subcategories in these also, like in voltage source there are two subcategories, one is ideal voltage source and second one is practical voltage source, that is written here, ideal and practical voltage source. So, if we say it, what is ideal voltage source? It is a source which is having two terminals and it provides a constant voltage across its terminals, which is independent of the load current. That is a property associated with ideal voltage source. So, this is the symbol for ideal voltage source, or this is also the symbol for ideal voltage source, or this may also be represented by this. So, what is important point in this? In ideal voltage source, internal resistance is 0. Internal resistance is represented by small r, that is 0 for ideal voltage source. And on account of that, the terminal voltage is constant. Whatever is the current passing through the source, terminal voltage is constant for ideal voltage source. So, that means to say the voltage across these terminals, that will be constant value, which will be the equal to source EMF. How much current? It may be a large current, or it may be a small current, or it may be a no current. All the time the terminal voltage will be constant equal to source EMF, and this is due to basically the internal resistance is 0 for ideal voltage source, and that is why we are getting these characteristics for ideal voltage source. On this axis we have current passing through the source, and on this axis we have the terminal voltage of the source, so, which we call source voltage may be there. So, this terminal voltage, that is equal to source voltage here, that is constant throughout whatever is the current passing through this source. On the other hand, we have a second subcategory of voltage source, that is practical voltage source or non-ideal voltage source. This can also be said as non-ideal voltage source. Non-ideal or practical voltage source. So, if we see the difference between the two, that means ideal voltage source and practical voltage source, what is the difference? That we can see from the diagram. Here it is having some internal resistance, this R, which is non-zero, finite value but non-zero, while in case of ideal voltage source that was 0. And this internal resistance, which is non-zero here, that is connected in series with this voltage source, and on account of this, the terminal voltage across the terminals of this source, if we find it, suppose it is V dash, so that will not be equal to source voltage, that will be different from that on account of this. So, suppose I is the current passing through this source, that time the terminal voltage V dash, that will be written as V minus IR, where I into small r, that represents the voltage drop in the internal resistance of the voltage source, this non-ideal or practical voltage source. So, from here, from this equation we can see, if current I is 0, that time terminal voltage will be equal to source voltage, but if current I is increasing, that time terminal voltage will decrease accordingly. So, these are the characteristics for this. This is the characteristic shown by this yellow green line. On the x axis we have the current passing through the source, and on the y axis we are having this terminal voltage. So, this green line, that is representing that with the increase in current passing through the source or current supplied to the load which is connected across the source, when this current is increasing, the voltage across the load or the terminal voltage of the source, that is reducing with that. So, this is the characteristic for practical or non-ideal voltage source accordingly. So, next we have the category for current source, that is another type of energy source. Basically, the energy source means which are providing energy to the circuit, those are known as energy sources, or we can say they are categorized in voltage and current sources. So, in current source again we have two categories, ideal and practical or non-ideal current source. This is the symbol for ideal current source, this is also the symbol for ideal current source, and the speciality of this, it is having internal resistance infinite, which is connected in parallel. That is the characteristic of this. This is shown by this diagram, that the internal resistance Rp, that is representing the internal resistance for this ideal current source, this is infinite, and connected in parallel to the source. On account of this, the current supplied to the load, suppose some load is connected here, load resistance I connect here some load resistance. So, the current supplied to this load, that will be constant all the time, whatever is the value of load resistance. It may be a smaller value of load resistance, it may be a larger value of load resistance, but source current will be constant, since this current, all the current from the source that is passing through this load resistance, this is not divided at any other place. This is basically due to the reason the internal resistance of this ideal current source is infinite. While in case of practical current source or non-ideal current source, if we see, this is practical current source or non-ideal current source. What happens? It is having finite value of internal resistance. This is Rs, which is the finite value of internal resistance, and that is connected in parallel to this current source. Is is the current for this current source. This is represented by this arrow that represents the current direction passing in this circuit. Similarly, in this case also, this is the direction of current. Here it is the direction of current passing in the circuit. But in case of non-ideal or practical current source, the internal resistance is finite value rather than infinite, which was the case of ideal current source, and this resistance is connected in parallel to the current source. So, on account of this, what happens? Now, the current is divided in two different branches. One is some current will pass, current will be going through the internal resistance of this source, and remaining current will go through the load resistance, which will be connected across the terminals of this source. Suppose this is RL. So, now the current which will go through this RL, that will be given by the relation I, this is suppose current I, which is passing through RL. So, that current will be given by Is, source current, into internal resistance of the source Rs upon Rs plus RL. This relation is found out using parallel current division rule. Since Rs and RL, these are connected in parallel with the current source. So, on applying parallel current division rule, we can find the current in any parallel branch. So, the current I will be given by Is into Rs upon Rs plus RL, where I is representing the load current in load resistance. So, here we can see with the increase in load resistance, this current passing through the load, that will be decreasing or that will be reducing with that. So, on that basis, we can see the characteristic of this. In ideal current source, since the internal resistance is infinite, current is constant in load resistance. So, this is the characteristic for ideal current source, current is constant, current delivered. While in case of practical current source or non-ideal current source, the internal resistance is infinite, connected in parallel with the source. So, that is why with the increase in load resistance, the current passing through the load, that will decrease. That means, mathematically what I can write, with increase in RL, the current in the load resistance will decrease, and that is accordingly this is the characteristic for practical or non-ideal current source. So, that way we represent this ideal and non-ideal current source. Next, we have another thing which is important before going further. This internal resistance of ideal current source is a large value. Internal resistance of non-ideal current source, that is a large value, while in case of ideal current source, that is infinite value. And similarly, internal resistance for ideal voltage source is 0, while for practical voltage source, internal resistance is a small value. These are some important things which are, or important points or characteristics associated with these sources. Next, we have Kirchhoff's laws. So, if we see the Kirchhoff's laws, what are the different laws given by Kirchhoff's? There are two laws basically which are given by Kirchhoff's. One is Kirchhoff's current law, that is in short we write it KCL. And second law which is given by Kirchhoff, that is KVL, Kirchhoff's voltage law, that we will be discussing in the coming slides. So, first we discuss Kirchhoff's current law. What is KCL, Kirchhoff's current law? So, if we see the statement is basically the algebraic sum of all the currents meeting at a junction is 0. This is the statement of KCL, Kirchhoff's current law. Now, what is node? Node means a junction point, or junction point is node, anyway we can say. Another thing which is important, this KCL or Kirchhoff current law, it is based upon the law of conservation of charge. That means charge is conserved in the circuit at any junction point or node. So, if we elaborate it further, what can we write, or what can we say? The sum of the currents entering at a node or junction point, that is equal to the sum of the currents leaving from the node or junction point. Like this example, that is elaborating all these things for Kirchhoff current law, KCL. This is a junction point or node in this circuit. Now, here 4 branches are meeting at this junction point. In one of the branch, IA current that is entering, in another branch IB current that is entering, in third branch IC current that is leaving or going away from the node, and in fourth branch ID current that is going away from the node. This is the node or junction point. So, now as per KCL, we have sum of the currents entering at a node is equal to the sum of the currents leaving from the node. So, IA and IB, they are entering current. So, sum of these currents IA plus IB, that is equal to the sum of the currents leaving from the node, that is IC plus ID. That way it is there. Or another thing that we can write IA plus IB plus minus IC plus minus ID, that is equal to 0. As per convention, what we have, the current entering to the node, that is taken as positive, while current leaving the node or going away from the node, that is taken as negative. That is why IA and IB, these are the entering current or current coming to the node, they are taken as positive here, while IC and ID, they are current leaving the node or going away from the node. So, that is why they are taken as negative. So, we can write in this form, and this is basically what is this: algebraic sum of all the currents meeting at a node is 0. As per this, algebraic sum of all the currents meeting at a junction is 0, or symbolically we can write it sigma I equal to 0. So, this is KCL, Kirchhoff's current law. And why this law is based on the conservation of charge? Since we write current is given as flow of charge per unit time, dq by dt. So, when we have seen here that whatever is the current entering to the node, same is the current leaving from the node. So, we can say whatever is the charge coming to the node per unit time, same is the charge going away from the node per unit time. So, that means there is no accumulation of charge at the node, and this is elaborating this principle that this KCL is based upon law of conservation of charge. That way we have this in any circuit, electrical circuit. So, like we take some numerical example for this. In this circuit, we have this node or junction point. At this junction point or node, 6 branches they are meeting, and currents are given in different branches. Like this branch is having 4 ampere current entering to the node, this branch is having 2 ampere current entering to the node, this branch is having 6 ampere current entering to the node, this is having 9 ampere current entering to the node, and this branch is having minus 1 ampere current leaving from the node, and this branch is having Ix current leaving the node. And we want to find what will be the current Ix with the help of KCL, that is Kirchhoff current law. So, as already we have seen that algebraic sum of all the currents, that is 0 at any junction point or node, or in other words we can also see that sum of the entering current is equal to the sum of the leaving current from the node. Anyway, we can find this unknown current Ix in this branch. So, we can write 4 plus 2 this is 4 plus 2 plus 6 plus 9, since all these are the entering current to this node. So, that is why they are taken with positive sign, while minus 1 ampere, that is the current leaving from the node. So, this will be written as plus minus into minus 1. This is basically plus into minus 1. Reason being, this is the current leaving from the node. plus minus Ix, since this is also the current leaving from the node, and that will be equal to 0. So, this is as per the result that algebraic sum of all the currents meeting at a junction point or node is 0. So, if we simplify it, we can write 4 plus 2 is 6 plus 6 12 plus 9 21, 21 plus this minus into minus 1 is plus 1. So, 21 plus 1 is this, and this is Ix on this side when we are taking Ix on the other side. So, Ix will come out as 22 ampere. So, that way we find what will be the value of Ix, which is unknown current in the branch. So, if we see it, Ix will come out as 22 ampere. So, that way we do it, that we can find the current in any branch with the help of KCL. What we are to do? We are to see what are the different branches which are connected at the junction point or node, and what are the currents in those branches. Another thing, whether those currents are entering in those branches to the junction point, or the currents they are going away or leaving from the junction point. All those things we are to observe, and then we are to form KCL equation as per KCL, Kirchhoff's current law, and that way we are able to find the current which is the unknown current in any branch which is meeting at the junction point. This is the method for application for applying KCL in a circuit at any node. Now, next we have KVL, Kirchhoff's voltage law. So, first is the statement. What is the statement of this? According to this, the algebraic sum of all the voltages around a loop or around any loop, that is 0. So, what is the procedure? Beginning with one node in the loop, add all the voltages across each branch in the loop, and then what is there? Algebraic sum of all the voltage drops minus algebraic sum of all the voltage rises, that is 0. This is KVL basically. Or we can also write algebraic sum of all the voltage drops is equal to the algebraic sum of all the voltage rises in the loop. Or this can also be written as sigma IR. This is the algebraic sum of IR drops or voltage drops, since IR means voltage drop, and sigma E, that is the algebraic sum of all the voltage rises, since E, this is the source EMF or the battery EMF. So, this is basically voltage rise. So, that means sigma IR equal to sigma E. This is KVL mathematically. So, like for example, for KVL we take this example. Here in this circuit we have this voltage source of 12 volt with positive terminal on upside and negative terminal on downside, one resistance of 7 ohm that is connected, another resistance of 3 ohm that is also connected. Now, this 7 ohm resistance that is connected across the terminals A and B, while this 3 ohm resistance that is connected across the terminals B and C, and this voltage source or battery of 12 volt that is connected across the terminals A and C. Suppose I is the current passing through this circuit. So, this is a closed loop or mesh which is there in this circuit. So, we can apply KVL that already we have discussed in the previous slide. What is KVL? So, by Ohm's law, VAB, the voltage across terminals A and B, that will be given by current into resistance, so I into 7, since I is the current passing through this 7 ohm resistance. Similarly, VBC, that is voltage across B and C terminals, so that will be given by current into resistance, so that is I into 3, since 3 ohm resistance that is connected across the terminals B and C. So, further if we see, by use of KVL, we will write the equation, KVL equation, which is VAB plus VBC minus 12 equal to 0, where VAB and VBC, they are the voltage drops, while 12 is the voltage rise. And in the previous slide, we have seen that sum of voltage drops minus sum of voltage rises, that is 0, equal to 0, that is KVL. So, accordingly we can write this equation, or we can also write it as VAB equal to I into 7, that we have seen already this equation. Similarly, VBC, that is I into 3, that is already we knowing, and so the equation becomes I into 7 plus I into 3 minus 12 equal to 0. This is KVL equation for this loop or the mesh. So, from this I into 10 equal to 112, that is the equation. and finally from this we can get the value of current I, that comes out as 1.2 ampere. So that way, by use of KVL or by applying KVL in the circuit, or basically in the loop of the circuit or mesh of the circuit, we can find the current in the loop or mesh, plus we can find potential drops or voltage drop in the different branches of the loop. And both the loop and mesh, they are closed path in the circuit. And there is a basic difference between the two, loop and mesh. Mesh is the smallest closed path, while loop, that is also a closed path, but that may be bigger than mesh, since mesh is the smallest closed path which is there available in the circuit. That is the difference. So whenever we are applying KVL in a circuit, so this is applied in a closed path which may be a mesh or which may be a loop. Another important thing which is there in the KVL, basically this KVL, Kirchhoff's voltage law, this is based upon energy conservation principle. Energy conservation. Why it is based upon energy conservation? That we can see. KVL is based upon energy conservation principle. Since we can see in this loop where we are applying KVL, whatever is the electrical energy delivered by this active element, which is 12 volt voltage source or battery, same is the energy delivered to these passive elements, that is 7 ohm resistance and 3 ohm resistance. These are passive elements, that already we have discussed what is active and passive element. So that means here in this loop, whatever is the electrical energy delivered by this active element, same is the energy supplied to these passive elements of 7 ohm and 3 ohm resistance. So there is no loss of energy at any point or at any place in this loop. So that way energy remains conserved. So that's why we say KVL, that is based upon energy conservation principle. So this is the how we apply KVL in a loop, and what is KVL, plus on which principle KVL is based. So this is all about this. Thank you. In the next lecture we will meet for another topic.